So, dear participants, good evening to all. You are all welcome for day 3 of FDP. Now, it is my privilege to welcome Professor Dr. Shanmuga Vadiyu ma'am to deliver the FDP session 3 on quantum error correction. Dr. R. Shanmuga Vadiyu is a professor and head of Department of Computer Science and Applications at the Gandhigram Rural Institute, deemed to be university. She has over 33 years of academic and 23 years of research experience. Her research area is medical image analysis, healthcare analytics, parallel computing, software engineering, content-based image retrieval. Ma'am guided 9 PhD, 21 MPhil scholars. She has published 60 papers in international journals, 50 papers in international conferences, 44 papers in national conferences, 3 book publications, 24 book chapters, edited 5 volumes. She has delivered various invited talks at national and international level. She is an editorial board member of various journals. She is a recipient of Indo-US 21st Century Knowledge Initiative Award in 2015 on augmenting the curriculum of higher education institution with an online integrated cognitive-based employability skills assessment system using signal and video analytics. She has received research funding of 2 crore 40 lakhs for research projects from various agencies like UGC, USIEF, DST SERB, ICMR, PMM, NMT. I request Dr. Shanmuga Vadiyu ma'am to deliver the session.
Thank you, ma'am. Thank you for your words and thanks for the introduction. I'm indeed so delighted to get connected to JAIN University. And this is the first kind of introduction we have between Gandhigram University and JAIN University. So I strongly believe this association should continue in the coming days and also should lead to better research outcomes. So very good evening, all of you. I should appreciate the kind of spirit that is held up by the organizers as well as by the participants. And as you all know, this quantum computing is gaining a lot of momentum. And as we just turn the pages of Google, we get to see a good number of conferences, workshops, seminars are focusing on this quantum computing. And it is interesting to know that you are attending an AICTE training and learning academy sponsor, that is the ATAL 1 week online faculty development program that enables participants to get connected across despite their geographical locations. So I should thank the organizers for having allowed me to handle session of today's evening because they have rescheduled it for me. I thank them for that as well. So without much delay, let me please permit me to share my PPT. One second. So can I upload my PPT?
Yes, ma'am, you are able to share, ma'am.
Okay, right.
And ma'am, your video
sharing is not turned on. The host is allowing sharing for this meeting. I think you have to set the
Ma'am, your screen is visible.
Is it done?
Yes, ma'am. But ma'am, go to PPT, ma'am.
Let me check.
Yeah, ma'am.
Yes.
Ma'am, the mail I have sent you, na, that page is visible, ma'am. Gmail.
Um, no, like I have to upload my PPT, right?
You have to share, ma'am. You have to share.
Yeah. Actually, when I click onto it, it is showing your screen, I suppose.
No, ma'am, it's not mine, ma'am. Actually, your
Oh, it's
Gmail.
not yours?
No,
Okay.
ma'am. It's Gmail account of yours is open, ma'am. Go to, ma'am, that
Okay.
tab where you have uploaded PPT, ma'am. Where
Yeah,
you
one
have
second.
opened the
I'll
PPT.
just try it.
Yeah, fine, ma'am. No
Right.
problem.
Thank you. See, when I give entire screen, it just comes out. Yes. Let me check.
Or, ma'am, if there is any problem, you can give us. We will only share from our end.
Okay, let me check.
Fine, no problem.
I'll open the PPT. Please check whether it is visible to you.
Ma'am, you have to, yeah, now it's visible, ma'am.
Visible, right?
Yeah, ma'am, and it should be, ma'am, slideshow.
Thank you.
Yeah, thank you, ma'am.
Right.
Yeah,
It's
yeah,
perfect, right?
perfect, ma'am.
Right, thank you. Yes, so today we are going to have a very interesting topic, that is quantum error correction. So I think the earlier sessions that you had on quantum computing must have given you enough and more opportunities to understand the essentials of this quantum computing, because this is a very interesting topic. And with a little bit of understanding about the principles of quantum computing, what do you exactly mean by BRA, what do you mean by KET, and what are the operations possible, what is polygate, and how do you perform operations, and what is the basic circuit like. If you just understand the basics, right, this makes quantum computing very interesting. In addition to that, mm, apart from gaining knowledge on this domain has got a good amount of potential to pursue research in an entirely new direction, and incorporation of this quantum computing will definitely give us an edge over the rest of traditional computing, and on par with artificial intelligence. And also, I think you all must be knowing we have quantum AI as well, quantum artificial intelligence. Okay, so getting into our topic, what is quantum error correction? So this quantum error correction that we shortly call as QEC, we'll be referring to this acronym across the PowerPoint slides, is a technique that allows us to protect quantum information from errors. Okay, see now when we just work with our modern computers, like digital computers, the probability of your data to get corrupted, and a zero being replaced by one, or one being replaced by zero, um, it seldom happens, because it is protected in such a way that, and the probability of flipping between zeros and ones, 0 to 1 or 1 to 0, absolutely never happens unless your hard disk gets corrupted, and when that something really goes wrong with the content, when there is a lot of bad sector where you're not able to open. So this kind of errors really do not happen in the case of modern computers. But when we start work with quantum circuits, it's quite possible to have a lot of error to get included, because it works on the principle of entanglement, and a single particle can be in a different state simultaneously. So with respect to the superposition and entanglement and the basic principle of quantum computing, it's quite possible error may creep in at the time of your operation. So error correction is especially important in quantum computers, because efficient quantum algorithms make use of large-scale quantum computers. So when someone is going to use quantum computers, then it's very important to take into consideration what are the possible quantum correction errors that could be taken into consideration to handle this problem of quantum errors. So which are sensitive to noise. Okay, so the basic principle, the number of bits used to encode a given amount of information is increased, right? So what happens, like in the case of quantum error correction, if you do not have the component called quantum error correction, so we are going to confine only to our data and nothing else. Whereas when you have to incorporate this quantum error correcting code also, ultimately the number of bits that are used to encode a given amount of information will automatically increase. I think because we have already learned about the basics of digital computers, wherein we talk about cyclic redundancy error, then error correcting, Hamming distance, all these things we've already seen. And nevertheless, those kind of error correcting codes also find place when we talk about this quantum error correcting codes. Okay, the number of bits used to encode a given amount of information ultimately increases when we have this component of error correction along with the original data. So this redundancy allows the code to detect and correct errors. Right? So the error rates of quantum computers, this is the kind of statistics we have got, are typically higher than classical computers' errors due to the challenges associated with building and operating quantum systems. See, like as we go by the basic principle of working with quantum computers or the basic principle of working with classical computers, the probability of getting errors in quantum computers is almost zero, which is not so in the case of quantum computers. So, noise, decoherence, and imperfections in quantum gates can cause errors in quantum computations. So this is the scope, like why should we learn about quantum error codes? So quantum error, I mean, quantum computers have the error rates. This is kind of rate in the range of 1% to 0.1%. So what do we really mean by this? Precisely, this means that on an average, one awareness may result in an error. So this is what we understand. So this situation, this case calls for learning about what are the possible quantum error correcting codes and how the errors can be corrected. Okay. So why do we need error correction code for quantum computers? See, the modern, like classical digital computers, or all of them, all intent and purposes, they are ultimately error-free. But the same cannot be taken into account when we talk about quantum computers because it has a lot of potential for error to get included because of the basic Am I audible?
Yes, ma'am.
Okay. Was there any problem in between? Did it get disconnected by any chance?
Yes, ma'am, you got disconnected.
Yes, ma'am. Yes, ma'am.
Okay. Okay, we'll continue again. There was heavy rain at Dindigul last night, like it was raining like a hell. So there is some problem in the network. So hope we do not get any such problem till we complete this. Okay, please call over the phone if this gets disconnected because I will not be knowing, like I'll be just continuing. Okay. 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 So we were discussing about the classical. Am I audible now?
Yes, ma'am.
Hello?
Yes,
Okay,
ma'am, you are
thank you.
quite audible.
So modern classical digital computers. Thank you. Thank you so much. So now we are just comparing between modern digital computers versus quantum computers. So even though near-term hybrid quantum classical algorithms have been conceptualized to achieve classically interactable simulations, right? Even in the presence of noise, it's becoming increasingly apparent that some amount of error correction is very much crucial to achieve satisfactory performance, because if the data is going to be encoded wrongly because of the intrusion of noise, then ultimately it is going to affect the accuracy of the result or performance of the entire algorithm. So more fundamentally, in order to assert that quantum algorithms will indeed achieve super classical performance in practice, it is very much important to understand the asymptotic significance of quantum errors and possibly the efficiency of correction. So how best we can incorporate how to understand the error and how to handle those errors. Okay, next. So quantum noise. So quantum noise models are mathematically explained this way. It is or mathematical descriptions of errors in quantum systems, and essentially for simulating and understanding their behavior. Right? Suppose if we talk about this quantum state reconstruction of this form, right? So you have this state reconstruction. So one state is being reconstructed with the help of these kind of representation. In such a case, when you have this kind of a state that has to be reconstructed with the two different channels, like, so the noise classification is going to be noisy channel A as well as noisy channel B, that is the channel through which you have got the operation done, and each channel may be prone to noise, and hence we pictorially represent like noisy channel A as well as noisy channel B. Okay, so now what are the different kinds of quantum noise models that we should be familiar with? The first one is depolarizing noise, and the second one is amplitude damping. I think I just take it for granted that you must be familiar with what is the amplitude, what is the phase about a quantum computing. So depolarizing noise, this model explains the entire process where the qubit is randomly changed into a completely mixed state. So like suppose when one particular component, when it changes from its own state to some other state, then the kind of information that is represented by that particular component is lost, right? So that means that that contains no information. So the qubit has the probability of being unaffected and a complementary probability of losing its information. So now, what we are going to see, like suppose that the problem of having this depolarizing noise is present, right? How are we going to manage it? So the next one is amplitude damping. Like this is the type of noise model that speaks about a loss of energy of a particular quantum particle. See now, what do you mean by this? What assuming by taking energy, one component can get excited, it can move from ground state to excited state. Like it will be able to like revolve, and that may represent different state. Suppose if the energy is being lost, what will happen? From the excited state, it comes down to ground state. So this type of noise models the loss of energy from the qubit to its environment, causing it to relax from an excited state, like when it possesses. So but when there is a loss of energy, what happens? It relaxes from an excited state to a lower energy state, something like the ground state. So that is what we call as amplitude damping. Then the next one is phase damping, that is called as dephrasing. So this noise model accounts for loss of phase coherence. I think you must have seen the typical representation of a quantum component. Like you must be having alpha, you must be having the phase value. I mean theta. So you will be able to see what is the angle and how it is going to rotate. So now suppose if there is no phase, what will happen? That particular component will become stationary and there will not be any kind of possibility for rotation or to move from one phase to another phase. So the noise model accounts for the loss of phase coherence in a quantum system. So while the total probability of being in a given state remains constant, in the case of quantum computing, the probability of being in a given state should not be a constant component. That should be always a changing component. But here, when that becomes constant, the quantum correlation, that is the phase, is ultimately lost, which is detrimental to quantum computations that rely on these phase relationships, right? So like suppose if there is no phase component that is being shown, then that is taken as a noise because the quantum components particles are not able to represent themselves in the phase that they are supposed to be. So then thermal relaxation, this model specifically describes the process where physical qubit interact with their environment and exchange energy. That is, there should be some energy when there is a relaxation, something similar to the previous amplitude damping, and it loses the energy or it exchanges the energy. So it changes from one state to another state. So 0 may become 1 or 1 may become 0. So leading to thermal decoherence and loss of phase coherence over time. So this is what you call as thermal relaxation. Then the next one, classical 3-bit repetition. So this so
Hello,
this
ma'am.
encodes bits by repeating them, right? This is 0, 0, 0, and the trail of ones that is represented as 1, 1, 1. Yes?
No, ma'am, you continue, ma'am.
Hello?
Actually, ma'am, voice was lacking. You continue, ma'am.
Hello?
Ma'am, now you are audible, ma'am.
Hello?
Ma'am, you are audible, ma'am.
But like after every few equal interval, it is getting disconnected. I do not understand. Let's see.
No problem, ma'am.
Okay. So is the screen visible?
Ma'am,
Could you see the screen, ma'am?
ma'am, it's not visible, ma'am. Now it's visible.
Let me check.
Ma'am, it's visible, ma'am.
Thank you. So hope it continues without any further error. Okay. So we were at this point. So you have this code like a trail of zeros and trail of ones being represented like this. So this is called as like, let us see what do you mean by bit flip error. Flipping is changing 0 to 1 and 1 to 0. So I have my mobile next to me. If this gets disconnected, please give me a ring, right? I'll try to understand. Okay. Because we are in the full screen, I'm not able to like understand when the connection goes off.
Yeah, you know, ਘੱਟ ਵੀ ਇਹੀ ਰੇਟ ਪੈਣੀ 5 ਕਿਲੋ ਲੈਣ
So a bit flip error is one of the simplest type of one second, I'll just okay. The error that can occur in a qubit, right? It's analogous to the classical bit error, where zero flips to one, or zero changes to one, and one changes to zero. So I think all of you must be knowing about these notations. Like this is ket zero getting converted to ket one, and ket one getting converted to ket zero. Okay, so now with regard to this single bit flip error cases that comes into classical 3-bit repetition code. Now let us see case one. If you have the code word, right, get 000, and if there is no error, then it just reminds us 000. And with regard to if one qubit flips, right? Only one qubit flips. What happens then? It could be in the first position, or it could be in the second position, or it could be in the third position. So accordingly, if qubit 1 flips, you get this representation. If qubit 2 flips, you get this representation. If qubit 3 flips, you get this representation. So likewise for code word get 1, one, if there is no error, and if it is if as we have in the case of the other one, right? And suppose if it is the first qubit flips with respect to 111 get, so you have 011. If qubit 2 flips, it is 101, and if qubit 3 flips, it is 110. So now how we go about the error detection. Bits in the string are not identical, then it is taken as an error. So the error correction reset all bits to the majority value. This is a very simple approach that we use. For instance, when we have the values as 0, 1, 0, the most occurring bits are, components are 0. So all are getting converted to 0. In the other case, and the more number of occurrences are 1, so the remaining, the 0 is converted to 1, 1, 1. So this is a very simple error correction. So then what is a code detection? The smallest number of bit flips required to transform any two code word into one another. It's a very simple understanding, right? I'll come again. Smallest number of bit flips required to transform any two code word into one another, like as we have done earlier. So then the next one is classical 3-bit repetition code is like Hamming distance, which is speaks about taking into consideration the minimum number of bit flips to transform bit string A to bit string B, right? So if this is your starting point, then it should be like should be your destination. So the code distance determines two important components. We will be referring to this little later as well. Here, maximum number of errors which can be detected, and because when we talk about error code detection, then we have to think about correction as well. So maximum number of errors which can be detected is d minus 1, and maximum number of errors that can be corrected is d minus 1 divided by 2. So as it decided by the distance that we measure. So you have to decide about the value of d. Accordingly, we will be able to work. So then quantum 3-bit repetition code words. So to avoid errors, encode the basic states like ket 0 and ket 1 into a joint state of 3 qubits. The two logical basic states are, now you have got the logical state ket 0 logical, and then ket 1 logical, all the zeros 3 times, all ones 3 times. So therefore, the single qubit, right, ket pi is given as alpha ket 0 plus beta ket 1 is encoded as. Now, pi of L, the logical representation is alpha ket all zeros 3 times and beta all ones 3 times ket, that is equal to alpha. Here you know what is the 0, 0, 0. This is represented as 0 of L, and this all ones is represented as get beta of ones, right? This 1L. So we have just got this one. Then to continue in the same topic, the quantum errors, like as it flips, right? So x of get 0, that becomes 1. So x of 1 is equal to 0. So phase flip error, you know what is the z, right? That represent phase in your quantum representation. So now z ket of 0 is equal to 0 and z ket of 1 is equal to -1, right? So if both x and z errors can be corrected, more general errors can be corrected as well. So the first one speaks about like how it changes from state 0 to 1, and second one is talking about the phase, as we've already discussed. What do you mean by phase damping, right? So when it remains in one state constantly, that is called as phase damping. So then quantum 3-bit repetition code. So encoded states after a ket 0 1 0 plus beta ket 1 0. Hope I'm audible to you.
Yes, ma'am, you are audible, ma'am.
Thank you. Thank you. So accordingly, now this introduces an error which has got changed into alpha ket 0 1 0 flipping by 1 bit single. We are talking about single bit flip error. So now beta error has got changed. The middle bit has been changed. Okay. So now we have to go in for error detection. So do not measure individual qubits in the computational basis, because measure the symmetries of the states rather than individual bits, because we just go in combination of a collection of bits. So a typical example that we can quote here is parity of any pair of bits. So now we are going to go for even parity bit and odd parity bit. All of us are very much familiar with what do you mean by even parity, what is odd parity. So it is just an extension of this principle on quantum computers. And even parity are given as 0 0 comma 1 1, and the odd parity like 0 or 1 appears in a kind of in ones. In the case of the other one, it appears in even number. So now the distance of a quantum code, as we discussed earlier, that can be computed. The distance of a quantum code is a fundamental property that determines the error correction capability of a kind of code that you are using, and is defined as the minimum weight of an uncorrectable error. Right? Sometimes it is possible. You all must be knowing. To some extent, if the error is there, then we will be able to correct. Suppose if the entire string has got corrupted. We do not have any clue about what was the original message, what was the original data, what was the original string like. In such cases, that becomes uncorrectable error. A code with a distance d can be corrected up to d minus 1 divided by 2 errors. That we have already seen. So let's see what is the weight of an error. In quantum error correction, an error is often represented by means of poly operator. I think all of you must be knowing, like in the basics of quantum computing, they must have thoroughly explained what are the types of poly operations that you can apply in quantum computing. Like you have alpha x, then alpha y, or I mean sigma x, sigma y, or sigma z applied to one or more qubits. The weight of this operator is the number of individual qubits it acts on. Right? So that is how we fix the weight of an error. That is decided by the number of individual qubits it is going to act upon for correction. So for these kind of 3-bit representation operators, then we have got the weight as 1. Correspondingly, the table shows how to make use of the weight and the corresponding operator. So now we are just moving ahead with 3-qubit bit flop code. Now, I think all of you must be familiar with this quantum circuit. So the 3-bit repetition code guarantees to return the correct bit value. That is the very purpose of working on this quantum circuit. So long as at most one of the bits in the code is flipped. So as long as one bit is flipped, then we will be able to detect and then correct the error. So we now use this as an inspiration for 3-qubit bit flip code, which is an entanglement rather than cloning. So we just reuse the principle of quantum computing, and it is not like repeating or just replicating something which has been lost, that we call as cloning. So this is a kind of reinforcing the entanglement, which plays a role of the repetition. That is, we encode the computational basic states. So if it is ket 0, it is ket 0, 0, 0. Ket 1 represents ket 1 because it is 3-qubit 1, 1, 1. So which is achieved by means of this following circuit. So how do you get? It is alpha ket 0 and beta ket 1. You have got 3 lines. So you have got this 1, 0, 0. So based upon the combination, it is going to get activated. Okay, so this has the following action on an arbitrary qubit state. As you know, it is alpha on 0 and beta on, alpha ket 0 and beta ket 1, right? On this on the corresponding ket 0 2 times, like doing the operation twice, then that is going to correct it. And this, the one that you have got with one bit being flipped wrongly, you are able to get the original values with all zeros and all ones. So this 3-qubit bit flip code, like we can just go ahead further, and to detect and recover errors, we supplement the circuit with 2 ancillas, right? That we use for error detection. So here, the previous one, as you could see, this is, you have only the input channels, right? So now previously, when you use 2 channels, they're being called as noisy channels because the data can get corrupted. It's quite possible that the data will get corrupted. So in order to go for error correction, you can see here, just you can study this diagram for a moment. And the previous one was just representing the channel and the data that has been passed. But as we go ahead with this, the modified version, which includes the error detection as well as error correction, and what do we understand from this? You have another arrangement where we have got a provision for error correction, and then it goes further ahead with this error recovery. That is, whatever be the bit that was supposed to be like got corrupted, then that is going to get changed accordingly, and we are going to get back. We are going to recover back the corrupted bits. Okay. So from this, we talk about the bit flop. It can be one, flipping of one, and then the second place, then the third place. Like you have got this alpha, and the first one is like having data without any error, right? No noise condition. So this is psi 1, and then you have got this kind of represent 0, 1, 0, 1, 1. 0, 1. We have learned about like even parity as well as odd parity, right? So now we just talk about the recovery. Now we just talk about I circle times. And here, because there is no kind of any need for, there is no error at all. So we just take the identity like as such it is being taken. Whereas when it is in the first place, like we just use this X in the first place. When the error occurs at the second place, then we use here in the second place. When the error occurs at the third bit, then we just use this notation. So accordingly, when we do this recovery operation, then it is ensured that you recover the data back, your data as such, whatever that you have transmitted. So that is, we have made a comparative parity check measurement that tells about like only about the error, but not about the quantum state itself. So we are able to identify at which position the error has occurred, and accordingly we are able to just modify. We don't just go deep into what is the state in which the input is available. Like, so these measurements have not destroyed the quantum state, and they just help us to recover back the correct quantum state. Fine. Then the 3 qubit bit flip code. Further, we have taken few cases like when there is no error, and when there is error in qubit 1, when there is error on qubit 2, when there is error on qubit 3, how we have to go about. I think all of you must be knowing about the syndrome. The syndrome is a kind of code that we use in error correcting of quantum computing, with the help of which we will be able to recover the original data as such. So that's being called as a syndrome, right? So here we make use of two syndrome. One is M1 and the other one is M2. Already we have seen how we are assigning values for M1 as well as M2. So in the first case, it is just 0, 0. Then accordingly, you have just make use of 0, 0, 0, 1. I mean 1, 0, and then 1, 1, and then 0, 1. Okay. So for the first time, like when there is no error, then the given states are alpha ket 0, alpha plus beta ket 1. Like because it is 3 qubit, you have got 3 zeros and 3 ones. So what is the syndrome? We have like the syndrome here, we have got the corresponding representation. So these are the syndromes. You have got M1 syndrome and then M2 syndrome. Like now we are going to take, this is the first one is case 1, case 2, case 3 and case 4. So these values are going to be dealt again in detail. So the syndromes are M1 is equal to 0 and M2 is equal to 0. So the recovery identity, so do nothing, like there is no need for anything. So what about the final state? Final state is unchanged. So the state and final states are the same. Okay. So now error flips qubit in the first position. So what happens? Like alpha, it becomes get 1, 0, 0, then beta gets 0, 1, 1. So now the syndrome bit that takes the value as 1 and 0. So apply X on qubit 1. So now what happens? Now it restores, it performs operation on this, and this, doing this operation with this 1 and 1 will give you 0, and 0 and 0 will give you 1. So now you get the original values. So likewise, error on qubit 2, error flips qubit 3, because we have 3 qubit input. Now we are talking about position qubit 1, qubit 2, qubit 3. Like as we take this 0, 0, 0, this is qubit 1, this is qubit 2, this is qubit 3. Likewise here also. So case error on qubit 2, what happens? Now we take this as 1, 1 and we apply X on qubit 2, then correspondingly we restore the correct state. Then likewise the third category, where we have got error flips qubit 3 as 1, 0, 0, 1 and 1, 1, 0. So the syndrome bits are 0 and 1. Now the recovery is apply X on qubit 3, and then the correct state is restored. So this is how we are able to work, and that has been depicted by means of this diagram. So now you will be able to understand. So how do we apply this M1 and M2 through this? And we take this data as well, because it's a noisy channel, and it is quite possible to have no error or combination of 3 different error occurring in qubit 1, qubit 2 and qubit 3, and accordingly we perform operation and then we are trying to recover. So then we are going ahead with the 3 qubit phase flip code. What do you mean by this phase? So the 3 qubit bit flip code demonstrates how we can overcome two of the possible problems with quantum error correction that we previously identified, right? So what are the two possibilities? We can either use entanglement to enable repetition, or we can detect errors using parity check measurements that do not destroy the quantum information. That's very important. At any point of time, that should not allow the qubit to lose its information. So, however, we still have not addressed the fact that quantum states are continuous in nature. Okay, to begin to do this, what do? We will look at an error correction code for different types of errors, like the 3-bit phase flip code has following action on an arbitrary single qubit state. So previously we were talking about correcting with respect to parity bits, even parity and odd parity. Now we are going to go ahead with the phase component. So now suppose if we have alpha ket 0 plus beta ket 1, like that is repetition for 2 times, then you are going to have the representation as alpha of plus 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 beta of minus minus minus. So which is achieved by means of this following circuit. So now you have alpha ket 0 plus beta ket 1, then you have the corresponding representation. So you're going to have 3 different states, final states out of this circuit, that is talking about phase component of our qubit. So now, in order to handle the noisy channel and in order to handle the phase error that occurs, then we have to we have to change this accordingly. As we had in the previous case, we do make use of 2 syndromes, like here you could see here, and then the corresponding values are being taken. We do some kind of computation and then we try to recover. So this is the error detection phase and this is the error recovery. Okay, so now this ket plus is, this 1 by square root of 2 always is associated with the phase component in quantum. So now its ket plus is 1 divided by square root of ket 0 plus ket 1, that implies 1 divided by square root of 2, then this becomes minus, right? So this plus ket 1 becomes minus. So ket 0 minus ket 1, that is equal to, you represent this as minus. So whereas when we go for this ket minus, then the phase is getting changed. So what do you mean by this phase flip? Excuse me. So this plus becomes minus and minus becomes plus. That is, phase is getting changed. Excuse me. So now this has got changed this way. So that has been depicted by means of the other one. As you take this minus, then it is 1 divided by square root of 2, that is ket 0 minus ket 1. That will give you this as 1 divided by square root of 2, that is ket 0 plus ket 1, that becomes plus. That's the reason why we have shown here. Now this may have the representation as alpha plus 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 and beta minus minus minus. Okay, so thus we have, and suppose this PH flip stands for phase flip, and the first one no error, and the second one is error in qubit 1, error in qubit 2, and error in qubit 3. So all the pluses, like all the zeros are represented by pluses and all the ones are represented by means of minus. I think you must be knowing about upward acceleration and downward acceleration with regard to quantum principle. So now suppose if this gets, if the phase gets changed, what happens? Plus becomes minus. In the case of this, this minus becomes a plus. So now when we have this as the error, the data with error, then what happens in the case of this 0, 0, it is just identity, nothing to change. We can just retain the original input. So when you go for the first one, like, with regard to qubit 1, what happens? M1 takes the value as 1 and M2 takes the value as 0. So accordingly, we perform this operation. The Z stands for the phase component. So it is Z, then circular times I and circular times I. So this will help us to retain the original ket of 3 pluses plus, alpha ket of pluses and beta ket of minuses. Likewise, this is for position 2 and this is for position 3. So as we had seen in terms of zeros and ones, and the same thing is represented by means of pluses and minus. And in the previous case, it was X that represented the position. Because we talk about phase, it is represented by means of Z, like in all the other cases. But for the previous one, we are able to recover the original values with which we started. So case 0, no error, then the PH flip is equal to nothing. So encoded state, like this psi of 1 is equal to, like you have alpha ket of pluses and beta ket of minuses, and the syndrome is 0, 0, no error detected. So the recovery is do nothing, just retain the state. So then case 1, phase flip on qubit 1. So we take this, the one where we have got changed ones, plus I mean minus in the place of plus, and plus in the place of minus. So for which we use the syndrome as M1 is equal to 0 and M2 is equal to 0. We apply and then we are able to recover. So the same thing is being explained for phase flip on qubit 2 and phase flip on qubit 3. I think it's very, very similar to what we have done with respect to qubit places. So then the next one is sign flip code. So the sign flip code deals with, this is a kind of bit flip that's only a kind of error in classical computers, but in quantum computers, however, another kind of error is possible that is called as sign flip. Okay, so in the case of, our modern computers, we have to worry only about bit flip. But in the case of this quantum computing, sign flip is a kind of an add-on. We have to take due care about it. So through transmission in a channel, the relative sign between like ket 0 and ket 1 can be inverted, right? So it's quite possible to change it. So the original state of the qubit is psi of ket is equal to, you have this alpha 0 ket 0 plus alpha 1 ket 1. So this will get changed into what, like uh, this psi dash is equal to alpha 0 all pluses and alpha 1 all minuses kets. So now the SHOR code, I think everyone must be familiar with because as we learn about quantum computing, we just cannot miss this. So the SHOR, that is 9-qubit code, was the first quantum error correction scheme that was really proposed, and the error channel may induce either a bit flip or sign bit, that is the phase flip. So, or both. You know what do you mean by bit flip? You know what do you mean by a phase flip or sign flip? So the error channel may include any of these kind of errors. So the bit flip, sign flip, or phase flip, we only refer to the occurrence of errors in these kind of representations. So it is possible to correct for both types of errors on a logical qubit using well-designed QEC, that is quantum error correcting code. So one of the examples of a code that does this is the SHORS code, which was published way back in the year 1995. Now we are talking about quantum computing in the year 2025 at length, but the establishment just takes us way back to 30 years back. Okay. So since these two types of errors are the only types of errors that can result after a projective measurement, the SHOR corrects arbitrarily single qubit errors. So you can see here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we provide 9 inputs. So this is 9-qubit code. SHOR is a 9-qubit code. So you have got this 9 kind of representations. And this is the ultimate circuit for circuit diagram for SHOR code. So you can just take a look at this. So you have error correcting channel, and then we are able to get back the original value. The psi, whatever that you get, is getting recovered back. And correspondingly, each channel will give you the corresponding result of this entire process. So quantum circuit, to encode a single logical qubit with a SHOR code and then perform bit flip error correction on each of the 3 blocks. So what do you mean by 3 blocks? So there are 9 inputs. So we divide them into block 1, block 2, block 3. So we just handle them with respect to 1, 2, 3. That's what they mean by. So they perform error correction on each of the 3 blocks. So then under this SHOR code, we can discuss about code concatenation that involves embedding the output of one code into the input of the another. Like we just like we know what is meant by concatenation, we know what is meant by code embedding, as simple as that. So in the construction of the SHOR 9-qubit code, the two codes that are concatenated are the 3-qubit code for bit flips and 3-qubit codes for phase flip. So now hope you are able to understand. So I'll come again in the construction of SHORT's 9-qubit code, right? So there are 3 blocks. So out of this, 2 codes that are concatenated are, the first one is the original data. So 3-qubit codes for bit flips and 3-qubit codes for phase flips, because this SHORT is meant for handling a bit flip, phase flip, or sign flip. So you have this data here, and the first component is the data block, and the second one is for bit flip, and the third block or third 3 bits are meant for phase flip or sign flip. So the 3-qubit code for the bit flips, that is C of 3B, was described and is defined as follows. Let's go to the next one. So the short code, this is the notation that we're supposed to use. So this goes like C3 blocks is equal to span, where you have 3B of zeros is equal to 0, 0, that is ket 0, and 1 of 3B, that is equal to ket of 1s, and S syndrome of 3B is equal to Z1, Z2, Z3, and Z4, right? So where S of 3B are the code stabilizers. Similarly, 3-qubit code for phase flips, this P stands for phase, right? Is defined as C of 3P is equal to span of, and whatever that we have done, that should be done in terms of, here we take it as bit flop, that is represented by means of this B, and here it is phase flip, and that is represented by means of P. Right? So wherever you have 0, you are going to have plus. Wherever you are going to have 1, you are going to have minuses. And we have already seen how we are going to manage with respect to x1, x2, x3, and x4. Okay. So to construct the 9-qubit, the bit flip code is embedded into the code word of the phase flip code, and this concatenation maps the ket 03P code word of the phase flip code to the 9-qubit code word of ket 9 as follows. Like as you have this ket 0 of 3P, that is equal to plus plus plus. So what is the concatenation? Then ket of 9 is equal to plus 3 times, right, with respect to 3B plus, this is like we go for embedding, plus 3B and plus 3B kets. So altogether that is represented by means of this, right? You can see here, right? So all zeros here, all zeros here, all zeros here, as an illustration. So to continue with respect to this phase flip, where this ket plus 3B, that is equal to 1 divided by square root of 2, and then you have the same kind of notation in the logical state of bit flip code. So now we embed this bit flip into the phase flip as such. Similarly, the concatenation maps this ket 1 of 3P code word of the phase flip into concatenation into your bit flip. So now we just concatenate, we go for concatenation. So ket 1 3P, that is getting embedded like continuous representation, repetition of 9 times, which is represented as like ket minus of 3B, ket minus of 3B, ket minus of 3B, that is 3 blocks. 3 blocks of bit flips. So where minus ket 3B, that is equal to 1 divided by square root of 2 ket zeros minus ket 1. This representation already we have seen. So the code defined by the code word ket 09 and ket 01 is the 9-qubit shorts code with parameters 9, 1, and 3. Right? So rewriting this right hand side of the equation, like whatever we have seen before. Don't worry about this 41 and 42 because we have taken this content from a textbook. So in the computation basis, we get the following code space for shorts code. This is very important. So now we go in for we have C of this representation, whatever that we have got here with respect to the parameters. It is 9 comma 1 comma 3 is equal to span of ket 0 9 equal to 1 divided by square root of 8, right? Because we have to do it for 3 times, square root of 2, square root of 2, and square root of 2 multiplication. So ket of zeros plus ket of ones, we have them in the close bracket C. That is the same representation we have to have here. So plus all ket ones and all ket zeros plus all ket ones. So as we talk about the similarly for ket 1 9, the same thing, and wherever we have this plus, here it is minus. If it is plus, here it is minus, the same notation we have. So the stabilizer of the above code is given as, so S of stabilizer of 9 comma 3 comma 3 is equal to, you have got the representation as Z1 Z2, then Z2 Z3 Z4 Z5 Z5 Z6 up to it goes to Z8 and then Z9. So likewise, the same thing for the bit representation. It starts from X1, X2, it goes up to X9, X8, X9. So to talk further about this short code, already we have seen, right, the parity, even parity and odd parity. In the similar way, we have to understand what is the role of the short code in terms of this kind of representation. As you could just count 2, 4, 6, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So the error, suppose if it is in the first place, so then this all zeros, one gets changed. And suppose if it is in the two places, then this is the representation. This is with respect to syndrome S for X representations, and then for Z representations, you have got, like, when you find time, you can just sit and see how this is representing the exchange of flipping of zeros and ones. Okay. So then the next one is the topological code. This topological quantum code is a type of quantum error correcting code where logical information is stored in global topological features of the lattice of qubits. So, I'll show you a diagram, like, to understand the lattice. See, when you just look into graphs, you know what is lattice, what is edge, then, and what is the node, and many such things. So errors are local, affecting a few qubits, but logical information is protected because correcting it would require non-local operation like cutting across the whole lattice. See, now what they want to explain here is errors are local to the set of data that we are dealing with. So that affects only few qubits. So, but logical information is protected because correcting it would require non-local operation. Like, suppose if you want to correct it, like, so that may call for incorporating data from non-local components, like cutting across the whole lattice. So this makes them highly robust to local noises. So now there is a possibility that when we talk about this topological code, that helps us really to protect the data from getting corrupted. So surface codes belong to a broader family of so-called topological extension of your topological codes, meaning errors are detected and corrected using local stabilizer measurements on 2D lattice of qubits. You know what is meant by stabilizer? So local stabilizer measurements on 2D lattice of qubits. So the general design principle behind this topological code is that code is built on by patching together the repeated elements. Look, previously we were talking about embedding your bit flips as well as phase flips. But now we're just going ahead with how we can make use of the local stabilizer so that you'll be able to formulate a code which will really help the quantum to protect the data or information from errors. So it is one of the most practical and widely studied quantum error correcting code, that is the surface code. So then the next one is structure. like as we talk about the qubit arrangement, so we all know the structure, how it appears like. So the physical qubits are placed on a 2D grid like square lattice. So what are the two types of qubits? Data qubits stored in actual quantum information, that stores the actual quantum information, that is supposed to represent by having this superposition as well as entanglement, because one bit may represent multiple states simultaneously. So then the next one is ancilla. That is, you know what is syndrome qubit, right? Syndrome qubit is the one that we use when we want to go for error detection as well as correction. So this ancilla, that is syndrome qubit, is used for stabilizer measurements, right? So to speak more about the stabilizer, there are two types of parity check operations that are being used. One is called as the same kind of repetition in a different format, star operation, that is X type, check for phase flip error, Z error, and then it is the plate operator, Z type, which checks for bit flops, X errors. Okay, so then the error detection, the phase flip error changes the outcomes of the neighboring star stabilizers, and bit flip error changes the outcomes of the neighboring plaque stabilizers. So by looking into the pattern of syndromes, we'll be able to locate and correct errors. So whatever that we discussed with respect to the previous example of phase correction, this is just an extension of the same kind of representation. But however, the pictorial representation differs slightly with respect to the lattice. So as you see here, the A component, like, so you have got, am I audible?
Yes, ma'am.
Thank you. So here we could see these two nodes in circles and these two nodes in squares, and we have got connecting components represented by blue color as well as red color. Let us see what we really mean by them. So the surface code Ford cycle, this is called a surface code Ford cycle. This is a pictorial representation. The code qubit like D1 and D2 are represented by circular nodes. You can see, right, circles here. And the ancilla, that is the syndrome qubit, is represented, A1 and A2 are represented by square nodes, right? So now the red and blue edges, here you have got blue edges, here I've got red edges. So the red and blue edges depict controlled X and controlled Z operations. I think when you worked with poly gates and poly operations, you must be knowing about what do you mean by controlled X and controlled Z operations. So whenever we talk about X, that speaks about bit operation. Whenever it is Z, it is phase operation. So that depict controlled X, you can see here as well. Right? So from this, we can understand the code bit is D1 and D2, represented by means of circular nodes. So here we have got ket D1, ket D2. In addition to that, you have got this A1 and A2, which are called as syndrome, like ancilla qubits A1 and A2. So you have got this as the kind of correcting code. So ket 0, A1, ket 0, A2. So now we are going to work based on the principle of control X and control Z operations. So now by going for the different combinations, so you have got bit flip correction, detection, and then phase flip correction. And then you are able to get the results over here, right? Because your data as such is going to get manipulated by the entire process and get the result accordingly. So now let us see what do you mean by this B, right? And so the red and blue edges depict control X and control Z operations controlled on the ancilla qubits and acting on the code qubits, right? So this is an equivalent structure code Ford cycle in the form of a circuit representation or circuit notation. Okay, so now let's just look into this surface code Ford cycle. Already you have seen like how we can manage with X's and Z's. So the circles in the figure represent code qubits and the squares represent ancilla qubits, and the red edges represent controlled X gates and the blue edges represent controlled Z operations. Okay, the controlled operations are the gates with which the stabilizers of Ford cycle are measured. So already we have seen this is called as Ford cycle, the surface code Ford cycle. This is being called as Ford cycle. Okay. These control operations are the gates with which the stabilizers of the 4 cycle are measured. So ancilla qubit A1 connects to data qubit D1. See, it is very simple. Like A1 getting connected to D1, right? Then D1 getting connected to A2. Then A2 getting connected to D2. And D2 getting connected to A1. So you have got 4 cycle. So I'll come again. So these controlled operations are the gates with which the stabilized operations are going on. As we just start with, like stabilizers of the 4 cycles are measured. So ancilla qubit A1 gets connected to the data bit D1 and D2 via red edges and therefore measures the stabilizer X1, D1, X2, X D1 and X D2. Likewise, ancilla qubit A2 measures the stabilizers ZD1 and ZD2. That's with respect to phase flip. So the stabilizers of the 4 cycle XD1, D2, ZD1, D2 commute with one another and then they intersect non-trivially on the event number of code qubits. See now, what do you try to understand from this? Like as we take A1, like this is going to interact with this D1 and A2 also interacts with D1. And as you take A2, A2 interacts with D2 and this interacts with D2. So based on which we have got the notations where we have got X D1, D2 and Z D1, D2. So the stabilizer of the 4 cycle XD1, XD2 and ZD1, ZD2 commute with each other and then they intersect non-trivially on the even number of code qubits. Okay. So now what is the inference? However, as the 4 cycle has 2 codes qubits n is equal to 2 with 2 stabilizers m is equal to 2, the number of logical qubits it encodes is equal to k, that is counted as n minus m, that is equal to 0. So as a result of which you do not get any code out of it. So the 4 cycle is not in itself a useful code because it is not able to give any kind of useful information. So as you fix the qubit size is equal to, so n is equal to 2 and m is equal to 2 because it's equivalent to 0. So that's the reason why we just more attention towards classical linear code. So the classical linear code or error correcting code, when considered as vector over a finite field, like form of linear subspace. So now there should be an understanding how we can represent your quantum content into linear subspace. So this structure allows them to be described by generator matrix and parity check matrix, enabling a powerful mathematical tools like linear algebra for efficient encoding as well as decoding. Okay, so now the CSS, it is not a cascading style sheet. It is Calderbank Shor Stian code that is classically used to represent this notation as CSS. So are essentially pair of classical linear code that are combined together to create quantum error correcting code, right? That's we are going to combine Steens and Shor code together, right? And that is called as CSS. So when we refer to the classical linear code, that is we mean non-empty set, right? So C is a subset or equal to summation of n, where binary strings of length n for some positive integer n, so which must satisfy just one basic property. What is it? So if u and v are binary strings in C, that is which is one of the elements of C, then the string u plus v is also in C. That is the concatenation of u and v will be in C. Here, u concatenation v refers to bitwise exclusive OR of u and v. That goes without saying, right? So now, to continue further, so there are two matrices that can be associated with the linear code that make encoding and error detection and correction easier. So that is done with the help of two components, the one called as generator matrix and the other one is parity check matrix. So now let us see what's the purpose of the generator. So one way to describe the classical linear code is with a minimal list of code words that generates the code, right? Generator is the one which is used for generating the code. So meaning that by taking all of the possible subsets of these code words or XORing them together, we get the entire code, right? So either we take the entire set or we just perform XOR operation on them and try to get it. So C is equal to now alpha 1, U1, then you just go for XOR operations, and ultimately you get alpha 1 up to alpha M. You know what is M, you know what is N. In the previous case, we just tried. So stabilizer is M, and the number of qubits, it is N. So this is about generator. Let us see what do you mean by this parity check. So another natural way to describe a classical linear code is by its parity checks, meaning that the minimalist binary string for which the string in the code or precisely the ones whose binary dot product every one of these parity check string is 0. So previously we were using the kind of XOR, that is concatenation. Now we're just going for a kind of dot operation. So now that is the strings V1 up to VR are element of summation of N. That is, there exists a parity check string for the classical linear code C. If this condition exists, U should be an element of that is summation of N. What is U? As you have, that is U varies from you can see here. So U concatenation this V1, like then this goes V1 is equal to U concatenation VR, right? So that this entire value should be equal to 0. So this is how we just go for checking the parity check, and then we apply this principle around which the generator and parity check work. So let us see how this works. So example 1, 3-bit repetition code. So the 3-bit repetition code is an example of classical linear code. So in particular, we have, let us assume C is equal to 0, 0, 0 and 1, 1, 1, right? So here we had C is from say V1, V2, V up to VR we have. So now we have taken 2, and so it is C is equal to 0, 0, 0, 1, 1, 1. So with respect to the linearity condition, there are just 2 possible choices for us, like U and 2 other possible choices of V. Okay, so it's quite trivial to note here, like trivial matter to go through the 4 possible paths to see that we always get a code word when we take bitwise exclusive OR. So what are the possibilities we can have? So it is all zeros concatenation 0, all zeros concatenation 1, all ones concatenation 0, and all ones concatenation all ones. So what do you get? 0, all zeros here, the result, all ones here. So the result, all ones here, so all zeros here. So whenever there is some problem, then it's quite possible for us to get the code word with the help of this bitwise exclusive OR operation. So then the next one is, the previous one is an example for 3-bit repetition code. And then the next one is 743 Hamming code. So I think we are familiar with Hamming code because we have worked with when we talk about error correction in terms of data transmission, then we must have learned about this. So the Hamming code is an error correcting code that encodes 4-bit message into 7-bit code word, adding 3 parity bit to correct a single bit error. So hope we're able to recollect the component, like suppose when we have error correcting code that increases the number of bits to represent the entire data. We just saw in the earlier slide. So when you have to encode a 4-bit, that becomes 7. So now the 3 is the overload. So it achieves the Hamming distance of 3, meaning any 2 valid code words are different in at least 3 positions. Right? It achieves the Hamming distance of 3, meaning that any 2 valid code words are different in at least 3 different positions, right? Because as we see with respect to distance. So the 3 parity bits, when interpreted as a binary number, indicate the position of the single bit error in 7-bit code word, allowing the receiver to correct the error accordingly, right? So let us take the 743 Hamming code. So it is one of the very first classical error correcting code ever discovered, and it consists of 16 binary strings of length 7. So you have got it's arranged as 4 rows and 4 columns, so 16 binary strings, and the length of each string is 7. 1, 2, 3, 4, 5, 6, 7, right? So this is a classical example of one of that kind. So now let us take further. So how does it work? So the encoding operation, a 4-bit message is converted into a 7-bit code word first of all. So what has happened now, the 4-bit message, whatever that is present here, has got converted into 7-bit because we have embedded 4 bits for the purpose of error detection and correction. So the 4-bit message is converted into 7-bit code word. 3 parity bits are being calculated and inserted into a specific position with the 7-bit sequence. So the transmission, so encoding is done before transmission. 7-bit code word is sent across the communication channel. So what happens at the time of decoding? The receiver checks the parity bits to detect errors, and if all parity checks are corrected, the code word is assumed to be of error-free. Right? It's perfect, right? So if all the parity checks are correct, then the code word is assumed to be error-free. It is perfect. And suppose if an error is detected, the 3 parity check bits form 3-bit binary number, which directly points to the position of the bit. It's very interesting, right? So if the data is, if no error is detected, it's all perfect. Then don't have to worry about it. If an error has been detected, the 3 parity check bits form a 3-bit binary number from which we will be able to understand at what position the bit has got flipped. So, which directly points to the position of the flipped bit. The receiver then flips the bit at that particular identified position to correct the error. Then already we learned about the CSS, right? So the CSS codes are stabilizer codes obtained by combining together certain parts of classical linear code. So already we have learned about this, right? So, this is Calderbank, Shor, Stian's code. So our significant class of quantum error correcting code are named after the inventor Robert Calderbank, Peter Shor, and Andrew Stian. So now let us see this CSS code. So in order to define the CSS code, we must have 2 classical linear codes, C1 and C2, that satisfy certain properties. So here the conditions go like this. Like C1 must be an kind of a code that is n comma k1 linear code, and C2 must be an n comma k2 linear code in such a way that k2 should always be lesser than k1. So second condition is like it must be that C2 should be a subset or same as that of C1. Then if both C1 and C2 like can correct up to T times of errors, T errors, then the resulting CSS code will be N, comma, K1 minus K2. So that's the reason why we prefer to have K2 to be lesser than K1. So code that corrects up to T quantum errors, meaning that an arbitrary error confined to T qubits. Like so, in the previous case, we just confined our verification with respect to 4, right? So now it is with respect to T qubit. That is an arbitrary number. Okay, so let us see what is this STN code. The STN code is a tool in quantum error correction introduced by Andrew Stian in the year 1996. So it is a CSS code using a classical binary. This, you know what is 743, right? What is 743? Altogether, your code length is 7, out of which 4 is your input stream and 3 is your error correcting. So Hamming code to correct both qubit flip errors, X errors, and phase errors, phase flip errors, like sorry, qubit flip errors, X errors, and phase flip errors, Z errors. So the STN code encodes only, one logical qubit in 7 physical qubits and is able to correct arbitrary single qubit error. Out of the 3, we are able to identify which position it has got changed. So let us check matrix in standard format, and Hamming code H00H you have. So H is a parity check matrix of the Hamming code. That is the reason why, if you remember, in all the circuits, whenever we talk about this error detection and correction, we have this H to represent the Hamming code. So now we have got H is equal to, now it should be a 7-bit, right? 1, 2, 3, 4, 5, 6, 7. So it takes the matrix of this kind. You have like this. So the stay code, the stabilizer formalism allows us to define the code space of a stabilizer code by specifying its poly-stabilizing group. You know what is poly operation. So we can efficiently describe this exponentially large group by listing all sets of all combinations of its generators. So since the stay code encodes one logical qubit in 7 physical qubits, the code space for stay code is a two-dimensional subspace, and it is 2 cap 7 dimensional. It is Hilbert space, right? Like this is with respect to this H and the corresponding values. So stay code, so in a stabilized formalism, stay code has 6 generators. So 1, 2, 3, 4, 5, 6, right? So all I stands for the unchanged flips, and wherever you have X's, that represents the bit, right, where you can look out for bit flipping, and then likewise you have got for this Z flipping also. So 4, and it finds all possible places, like all 4 together at the end, and 2 in the middle and 2 at the end, and alternate ones here. So likewise you have got for this as well. So these are all the 6 different code which are being generated out of this TN code. So the logical X and Z gates are X logic is equal to all X's, 2, 4, 6, 7, all 7 X's, and Z logic is equal to all 7 Z's. So the logical ket0 and ket1 states of the stay code are, and this already we have seen with respect to phase flipping. Now, according to stay code, it is this ket0 of L is equal to 1 divided by square root of 8. That represents the phase component. So you have 1, 2, 3, 4, 5, 6, 7, right? You could see here, and all 7 bits like ket0, and then now this is a combination of modification of 1, 0, 1, 0, 1, 0, 1, and then you have got the other combination like so here you have to understand, and if it is 0, like this all zeros, this ice will represent 0, right? If it is X represents your bit, so in the places of X we must have changed, because X represents the bit flip and Z represents the phase flip. So wherever, suppose if you have them as 0, then in this place you must have 1s. So if this is 1, in these places you have to get zeros, and if this is 0, you have to get 1 here. Hope you're getting the point. So as you see here, if this is the original one, so what happens with respect to IEX, 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 I? This is what you get. So then plus the different combination 0, 1, 1, 0, 0, 1, 1, then 1, 1, 0, 0, 1, 1, 0, and plus 0, 0, 1, 1, 1, right? Then 1, 0, 1, 1, 0, 1, 1, then 0, all 4 ones, 0, 0, then 1, 1, 0, 1, 0, 0, 1, all possible combinations. So what does it do? It generates 6 generators. So then ket of L logic is equal to XL into ket of 0L. So arbitrary code states are of the form this psi ket is equal to alpha ket 0 logic plus beta 1, beta ket 1 logic. So this is the code, like this is how Stian has formulated it. So we have just understand this. So stabilizer codes are the fundamental framework in quantum error correction, and that uses additional qubits and measurements to detect and correct errors in quantum computations. So further, the stabilizer consists of a set of commuting operators that define valid code space, and that measurement that provides error syndromes. You know what do you mean by syndrome? Like, please remember that M1 and M2 to identify the correct errors caused by noise. Okay, making quantum computing communication like more reliable. So how stabilizer code works? Encoding, the logical qubit is encoded into a larger number of physical qubit, creating entangled states. And then, this poly operator, the stabilizer operator, a set of commuting poly operators like Z and X form stabilizer group, and these operations are associated with valid encoded state that we have seen with respect to an example. So what is the role of error detection? You know what is this ancilla, right? That call as syndrome qubits. Like wherever whenever there is an error correction, you have to introduce this, are used to measure the stabilizer operations. So the syndrome, yes? Hello?
Ma'am, you continue, ma'am. No problem.
Okay. Thank you. So which indicates the kind of error that has occurred without revealing the encoded information itself. Okay, so what happens with respect to correction? This is our focus, right? Based on the syndrome, the appropriate correction operation is applied to restore the original quantum state. So based on the syndrome and its corresponding positions, we are able to get it. So this is about the stabilizer code. In n qubit stabilizer code is specified by a list of n qubit poly operations. So P1 up to PR. So these operations are called as the stabilizer generators, and they must satisfy three properties which are given here. Point number one, and you can just the stabilizer operators all commute with one another, right? So like when you have one representing J and one representing K, so it is commutative. Like P of J. P of K is equal to P of K, P of J. So where J and K vary from 1 to R, because we have taken the poly operators from P1 to PR. So both J and K take the values between 1 and R. So the stabilizer generator forms a minimal generating set, right? So this is the second one. So P of K should not be an element of P1 and then Pk minus 1, Pk plus 1 and P of R, right? So for all values ranging from 1 to R. Then the third interesting condition is at least one quantum state vector is fixed by all the stabilizer generators. That is that satisfies the condition. Suppose when you talk about the identity like circle times n, that should not be an element of P1 to PR. So like when this condition is being satisfied and we just go for generator, then the first condition implies that it does not matter in what order the measurements are performed, right? The observable commute, so that measurements are also commutable. So the second one is the second condition requires that stabilizer generator form a minimal generating set, meaning that removing any one of them would result in a smaller stabilizer, because we have made a mention that that P of K should not be an element of the entire set. The third condition requires that at least one non-zero vector is fixed by all the stabilizer generator, which is equivalent to minus I times n not being contained in the stabilizer. So as we talk about the code, a simple example of stabilizer code is 3-bit. So totally, as we had 743, this is an example 3, 1, 3. So it encodes k is equal to 1, logical qubits into n is equal to 3. So physical qubit and protects against a single bit flip error. So this is our objective, right? It protects against single bit flip error in the set of xi. So now we have a G1 to represent Z, Zi and G to represent I, Z, Z. Let's see further. So if there is G2, commute, right? And the syndromes will be +1 and +1 and no error has been detected. So if there is a bit flip error, what happens? The first encoded qubit operator G1 so if if there is a bit flip error on the first encoded qubit operator G1 and that will anti-commute and G2 commute, then the syndrome will be -1 +1 because this is encoded, there is a bit flip error. So this is -1 plus and the error is detected. So if there is a bit flip error on the second encoded qubit, so it's very interesting, right? So then it is minus. So G1 will anti-commute and G2 also will anti-commute. So what will be the syndrome now? Now it is -1, and the error is detected. And if the bit flip error is on the third encoder qubit, then operator G1 will commute and operator G2 will anti-commute. So what will happen now? This is plus and then -1, and the error is detected, right? So this is how the stabilizer code helps us to detect it. So I will just look into this example, 9 qubit code. So it encodes 1 logical qubit into 9 physical qubit. So then it has the distance 3, meaning that it can correct. So when we have the distance, what does it mean? So it can correct any single qubit error. So that is X, Z, or Y. So here we have taken 9 qubit code. The notation is NKD. So N is equal to 9, that is 9 physical qubit. K is equal to 1, that encodes 1 logical qubit. And D is equal to 3, the code distance is 3, meaning that detect up to 2 errors, because you know it is D minus 1. Or correct 1 arbitrary qubit error, that is flip bit or phase bit. Any one can be corrected. So this is the example of 9 qubit code. Suppose when we take shorts code combines 3 qubit codes, 3 qubit codes of 2 in combination. So 3 qubit bit flip code to correct X errors. So it encodes 0 ket into this kind and 0 1 into ket 1 into this kind. So it detects and corrects bit flips. So a 3 qubit phase flip, what does it do? Already we know encodes ket 0 into this format and ket 1 into this format. So detects and corrects the phase errors. So by nesting them, shorts 9 qubit code protects against. So now we are going to combine these two. That will help us to protect both bit flips as well as phase flips. So the logical states are now ket 0 logic is equal to 1 divided by 2 square root of 2. Then you have the combinations of this kind, 0 0 1 1, then 0 0 1 1 and 0 0 1 1. So then 1L, that is represented because this plus is going to get changed into minus. So it is 1 divided by square root 2 square root 2, the same representation, the phase being changed. So each block of 3 qubit is fit flip code, and overall sign structure handles phase flip. Like we can see from here, the first one is for bit flip and the second one is for phase flip. So the next one is 7 qubit code. Example 1, logical qubit into 7 physical qubits. So has a distance 3 so that it can correct any single qubit, either bit flip or phase flip or sign flip. So in the CSS code, already we have seen that is the form of 743 code that we have seen. So then 7 qubit code, the representation is 7, 1, 3 that has got 6 stabilizers, generators, which can be expressed like this. So H is equal to H Hamilton code and this H and then 0. This is the notation. So where H ham is the 3 into 7 parity check matrix of classical 7, 4, 3 Hamming code, because we speak about in terms of 713. So the following are the 3 check operators that will detect bit flips. Like, so M1, you know what is this syndrome? M1, M2, M3 here. This is the notation. Then 3 check operators detect the phase error, M4, M5, M6 of this notation. So all are 4-bit representation. So you have got 1, 3, 5, 7, 4 positions. Z2, Z3, Z6, Z7, Z4, Z5, Z6, Z7, the respective positions in the 7 code. Likewise, here you have got M4, M5, M6. Okay, so the 7 qubit code, the logical states will be ket L, 0L is equal to 1 divided by square root of ket X, where X is an element of C. Already we have seen what is the purpose of this 1 divided by square root of X. We have already seen in the previous examples. Whereas ket 1L is equal to 1 divided by square root of X. Now X is an element of like X, XOR with 1, 2, 3, 4, 5, 6, 7 code, right? So that's why it is called a 7 qubit code. So where X is an element of C, right? After X we have taken, and now we are doing concatenation with continuous 1 7 times. Where C is the set of 7-bit code words, the classical Hamming code. So this we use for coding. So this means that a ket 0L is equal superposition of all valid Hamming code, that is as such the original input, and this is the one ket 1 is the same state, whereas a bit, all the bits are being flipped, right? So this is the two extremes, like without error with the maximum errors. So this 7-qubit, also known as Strian's 7, 1, 3 code, built from the classical Hamming code, that is we are able to understand, right? So from where this has been derived. Hamming 743 code, encoding one logical qubit into 7 physical qubits and correcting any single qubit code using CSS framework. Okay, so the next one is bosonic code. Can we still continue? I have got few more to go.
Ma'am, try to wind up because next speaker is waiting, ma'am.
Okay, fine.
Yeah,
So
ma'am.
in addition to that, we have got few more codes. I'll just leave it to you for your learning and understanding. So this is the this code is called as bosonic code, right? And then the next one is called as binomial code. We know what is the binomial operation. So that is based on this. This binomial code is also a family of bosonic error correcting code, right? So that works with respect to the principle of like that takes into account the photon loss, dephasing, and the gain errors. It is able to address all those things. Then this is the notation for binomial code. Then cat code is another one. This works on Schrodinger's cat states, and this is the notation. Like as we have already seen all those things, this is all only the extension of all those notations. So this cat code that makes use of two sets of states, that is as it is represented here with plus and minuses, and it works on photon loss and many such things. So I'm stopping here. So this is how we work with respect to quantum error codes, and this is how we implement. So as a researcher, we can just think of how best we may be able to probably change these kind of codes. Will we be able to come out with something which is more interesting than what we have discussed so far? And that is where our research lies, I suppose.
Yeah, thank you, ma'am. So I request ma'am and also the participants, could you please turn on the video so that we can take some pics? Just it is a formality.
Okay.
And participants, this session is now you can ask the question and answer. You can now you have to type this on chat window, or either we will unmute you and you can ask the questions from ma'am if you have any questions. Ma'am, kindly stop the sharing of screen, ma'am.
Oh, sure.
Yeah, ma'am. I request all the participants kindly please enable your video.
How many participants there are altogether? Oh, 153.
Yes,
It's a
ma'am.
good number indeed.
Ah,
Congratulations.
thank you, ma'am. Thank you so much, ma'am.
So participants are requested to switch on the video. We are taking a photograph for the AICTE submission.
That is very important than anything else. I think you can grow in groups like you can just have shots of, I mean, one after the other, right? In groups.
Yes, ma'am. Ma'am,
You can
that
go
is
for that.
that is done from our side. Now I
Okay.
request the participants, if you have any question, you can ask. The session is now open for question answer. Ma'am, now you can turn off, ma'am. No problem.
Yes. And they have asked about, please send the PPT. Sure, I'll share it with ma'am.
Yes, ma'am. Ma'am,
Definitely.
people like your session, ma'am. They are telling it's very informative and impactful session. And yeah,
Thank
ma'am,
you.
for us also it is very impactful. Let me, ma'am, deliver the vote of thanks.
Sure.
Yeah, ma'am. So it is my privilege and honor to extend the vote of thanks at the conclusion of this insightful session on the quantum error correction. First and foremost, I would like to express our heartfelt gratitude to our esteemed resource person, Dr. Shanmuga Vadiu, ma'am, for delivering such a comprehensive and knowledgeable session. Participants has gained a comprehensive understanding of nature of quantum errors, the necessity of quantum error correction, and the functioning of key error correcting codes such as the 3-bit flip code, 3 qubit phase code, sign flip code, shore code, surface code, STN code, stabilizer code, classical linear codes with examples. The resource person also provided a valuable insights into the challenges of fault tolerant quantum computation and the current state of research and development in this area. Thank you, ma'am, for this wonderful session.
Thank you. Thanks for all your efforts to get connected right from both ends. Like your messages, your communication, and everything really helped me a lot. Thanks for all your efforts.
Thank you so much, ma'am.
Thank you. Thank you, everyone. And I thank the fraternity of faculty members for your patience and presence. And this is a very interesting domain, quantum computing. Please take it forward. And that will help you to come out with good publications because there are very less number of publications which are available. So please do take care of these takeaways. Just don't leave them as such. And please do incorporate them in your research component. Those who are working with artificial intelligence, you can just go ahead with quantum AI techniques. Like you, for all the combinations, you have got the what do you call as quantum machine learning models, and then quantum once again. Yeah, so all quantum AI can be used. Like you have quantum decision trees, you have got quantum SVM, you have got quantum CNN, right? ANN, all those things are available. So please do take care of those kind of models because that will really help you to have a different flavor in your research work. Because there are only less number of publications available. Please do take care of that, right? Someone has asked me my contact details. I'll just share it. 944-37-36780. This is my WhatsApp number, 37367. I think the organizers will be able to provide you, but still, because they have asked.
Thank you, ma'am.
Can
Once
I
again, ma'am.
can I ask one question? Sorry.
Sure, ma'am, you can.
Yes.
As ma'am was saying about working with AI techniques like decision trees and all these quantum versions are available.
Sorry, ma'am.
Am I audible?
Yes, yes.
So you were talking about those people, those who are working in AI field.
Yes.
So they can make use of quantum techniques too.
AI models.
So yes, AI models, quantum AI models are there.
Yes, they're readily available. As you work
Yes,
with AI models, you can make use of them as well.
Yes. So what I was
And there is a
asking
scope
is
also
when
for
you are
us to.
Yes. So what my question is that when you compare this quantum AI models with normal machine learning model, how should
Okay.
that be like compared?
Yes, it all depends in what grounds you're comparing. Is it in terms of complexity? Is it in terms of time, or is it in terms of accuracy? If you want to focus, if your objective is to increase the accuracy, of course you can compare with the quantum AI with AI. And in terms
Is
of
it possible
complexity, this is quite easier for us because there is the computation aspect is faster in terms of quantum AI.
Is it possible like because I worked with some quantum AI models. So what happened in my case is accuracy of normal machine learning model was bit higher than the quantum AI models
Exactly.
for the same
Exactly.
data, but then time reduced.
Exactly.
So that does that happen usually?
No, it happens. Even for my scholar who was working with normal SVM and quantum SVM, the accuracy was less. But there's a scope for you to improve upon this, ma'am. And you just look for, I mean, from the literature, you read the papers, and then she was able to improve the accuracy. And because you have to change you should optimize them and you have to fine tune them, and then we were able to improve the accuracy. There is scope, and you have to just
Okay.
get hints from the literature on how it can be improved. Of course, we were able to achieve it. You will also be able to achieve it.
Yes, yes. Okay, okay. Thank you so much.
Thank you so
Thank
much,
you,
ma'am.
ma'am. Thank you.
Now it's my privilege to welcome next speaker,
Bye for
Dr.
now. Good night, everyone. I'm leaving.
Thank you, ma'am. Thank you. Now
Thank
it is my privilege to welcome next speaker, Dr. Kolla Bhanuprakash sir, to deliver the Day 3 FDP Session 2 on quantum computing in industry, application and case studies. Dr. Kolla Bhanuprakash sir is a professor and associate dean R&D at KL deemed to be university. He is an adjunct professor at Taylor's University, Malaysia. He has published 150 plus research papers in international and national journals and conferences. He published Scopus and SCI publications 100 with an H index of 23 and total citation of 2100. He is a reviewer for several international journals including IEEE, Elsevier, Springer, Ville, Taylor and Francis, and he has served as a reviewer, keynote speaker and TPC member for several international conferences. His research interests include deep learning, data science, quantum computing. He received the Best Researcher Award 4 times. He authored 3 and edited 15 books with internationally reputed publishers like IEEE, Elsevier, Springer, Elsevier, Springer, River, CRC, Nova, and Ville. He also published 15 patents, 2 patents grants, and 1 copyright. He is guiding 3 PhD research scholars. Under his guidance, 3 PhD were awarded. Dr. Bhanu Prakash is an IEEE senior member, fellow ISRD, and treasurer of ACM Amravati chapter in India, LMIST, MENG, SMIRED. He is a series editor of Next Generation Computing and Communication Engineering at Ville Publishers. He is a series editor of Industrial 5.0, Artificial Intelligence, Cyber Physical Systems, Mechanotronics, and Smart Grids, CRC Publishers. He is a NAC assessor. He is listed in top 2% of cited researchers worldwide by Stanford University and Elsevier for 2021. He received a grant of 27 lakhs from MEITY for establishing a quantum computing research lab, QCAL, at KLEF, and a grant of DST serve worth 5 lakhs for organizing a workshop and conference in quantum computing. He delivered many keynote speeches and expert talks worldwide on quantum computing, machine learning, and deep learning. I request Dr. Bhanu Prakash sir to deliver the session.
Yeah, thank you, Professor Taskeen, for that detailed introduction about me. So I would like to share my screen. I will keep my video switch off for bandwidth. Just to confirm, Professor Taskeen, can you please confirm you are
Your
able
PPT is visible, sir. It's quite
and
fine,
my
sir.
voice is loud and clear?
Yeah, it's fine, sir.
Thank you. Thank you. Yeah, thank you, everyone. So my session is a little bit different. Like it will be like what exactly is the requirement in industry after learning all the algorithms, you're learning the coding part, all the theory part you are done. Then what you are supposed to do going to industry? What is industry asking for? What are the different applications that you can solve? What are the case studies that you have to solve? So that are you really industry ready? So that you can be given an opportunity. In India, thousands of jobs are there ready, but manpower is not there. There are no students or faculty to get hired. Upskilling is readily required. So that is the reason after Professor Taskin invited me, I said like I will be taking this particular session so that it will be helpful for all the students and faculty also. So let us see. So quantum computing, I will not be giving that much of introduction, but what is exactly industry is asking for is to solve utility scale real world problems in business and in industry, like discovering molecular intelligence, unlocking chemical intelligence, accelerating decision intelligence, optimizing operational intelligence, okay, at a faster rate that is expected. Like if you have, for example, we have in pharma, many use cases are there. So you have to be ready to solve that particular use cases in pharmaceutical industry, like in drug discovery. Why? Because uh, a particular simulation which will be in solved in 1 week. Okay, in classical computing, we can solve it in nanoseconds for solving some drug discovery problems. That is the reason quantum computing is very essential in healthcare. Okay, for example, to perform conformer search, ADMET prediction, if you say, or single point energy, or tautomer search, or protein preparation, or ligand preparation. These are essential. And also like to solve some quantum chemistry problems like intrinsic reaction coordinate or geometry operation or potential energy surface scan if you take or frequency AR spectrum or reaction path search. These are things which you are supposed to simulate using a quantum computing simulators. And also you can also perform as a computer science student if you are there. Library optimization is one important use case, and reaction pathway search, molecular dynamics, protein ligand interactions, retrosynthesis analysis. These are some of the very important use cases where your deep tech technologies are required, and you should be very well aware of the full stack vertical integration of AI and quantum computing. Okay, so various applications are there where you are required, but you are not ready for that. So upskilling is required immediately to work in logistics and operations, financial services, aerospace and defense, transportation, smart cities, power and grid infrastructure, wherein like triple students also are required to work there. Okay, and you have energy and materials, manufacturing, even mechanical students who learn quantum, they are they are required readily immediately now for automotive supply chain management. Okay, so the IP IP is very important. Intellectual property is very important. So to achieve that intellectual property, first you should be well ready, okay, to program properly, to write the code on your own, so that you will be industry ready. And there are there are various opportunities are there. Okay, so India also is stepping ahead quickly so that it can match to the world. So this is a little bit introduction. So then, like you can see that some of the important things which you come across while doing this, like you emerge cross-disciplinary paradigms. You have to concentrate, like some particular case studies I have taken here, like space technology, biosensors, and VLSI design, where quantum computing is essential. So these three I will be going a little bit deeper, and I will show you the importance, which algorithms you have to study so that you can be ready for that. And I will show you some results also. I will show you. And hardware interface incompatibility may be there. So because semiconductor industry is growing quickly, so semiconductor industry and that VLSI and quantum computing can be integrated, then it will create wonders in India, right? So like semiconductor hub, a quantum computing hub also will be get created. Then we can do wonders. We can do everything in India itself. So the environmental sensitivity is also an important factor which you take for space research if you are taking up biological applications. And in quantum computing, the main problem that you generally observe is we observe more noise in this, and decoherence is a big problem. So you need to take specific care to avoid that quantum decoherence problem and error rates. So that major obstacles in long duration space missions And nanoscale biosensing applications, they require stable quantum state. So your algorithm should be robust enough to make it stable. Okay. There will be some limits will be there. So the physical realization of these devices to bring into these biosensors and velocity is still a major challenge. Still, it is in growing stage. So it will take some time. Like, as I said, like some challenges you will come across in doing these things, like how to integrate our quantum to classical. Okay, like, so support vector machine, you are done in machine learning, classical machine learning. The same quantum support vector machine you can also perform, and you can improve the accuracy by varying different parameters, so that those quantum machine learning algorithms can be applied in space research, biosensor research, VLSI research. Okay, so you should be very skilled enough to integrate with classical system. That's why your upskilling is required. The second thing is environmental stability and recurrence. As I said, this is a very big challenge. Okay, and to scalable these things to a uh, larger scale is very challenging. So there will be some space payloads. You can also should be implantable biodevices. You should show and dense VLSI layers. So they're technically demanding, but how good we are to solve that. Okay. So and material and fabrication compatibility will be there. That how you can make a superconducting CMOS. Okay, and biocompatible fabrication process, they are posing a lot of challenges for our manufacturing units. Okay, so the main important worry is lack of domain-specific quantum algorithms, which you are ready to implement them. So the algorithms, if I name a few very important algorithms which you can use for readily for VLSI or semiconductor designing, quantum VLSI. So VQ is one very good algorithm which we generally use mainly in many applications, even quantum computing in normal computer science student. They generally perform this VQ, variational quantum eigensolver, to solve numerous applications. And the same thing is also useful in VLSI for ground state energies. And for optimizing certain things like resource scheduling or sensor fusion, we generally use QAOA, one of the popular optimization techniques. A lot of papers, research articles also are published with VQE and QAOA. Even our students published, and my scholar also published a paper with a lab, with a output that we got it in our research lab. Okay, so the surface code is important so that error code comes less by qubit encoding, and how we will have to take care regarding the fault tolerance. So the like how you studied your principal component analysis in classical machine learning, the same eigenvalues, eigenvectors, convolution theorem, principal component analysis. Also, we have to perform in quantum so that efficient dimensionality reduction happens. Same like as I told you in mentioned before in the introduction, support vector machines and k nearest neighbors, what you studied in classical, the same quantum support vector machines and quantum k nearest neighbors. Okay, they're analogous for classification and pattern recognition studies, which people started using them. And another very important algorithm is Grover search, which we generally mainly use for image processing, and also we use for search strategies, like as main application for your own traffic reduction. Okay, so you want to reach a destination quickly, so you should know the plan, like a optimized route. So Grover's search algorithm is very useful, and the same thing can be applied for quadratic speed up in search tasks, and which is very useful for VLSI defect localization, which is still in early stage. If you are ready to write a research project in this, you'll be the first one who will be performing in this. A simple comparison, if you take it like, so the challenging areas, five mainly I have mentioned here out of research that I have carried out, like integration with classical systems. If you see, okay, so quantum algorithms that we will be using, okay, along with QAOA, the main use case where we use is like for adaptive satellite control and biosignal analysis with classical feedback. We can implement this on NISQ. The second one is environmental stability and decoherence. Okay, where our quantum error correction, like source code. So earlier speakers, some of them they would have mentioned you regarding the source algorithm. Okay, so the same source algorithm, how you can apply, how you can use for stabilizing quantum operations in radiation-prone environments, which is a very important application space and biosensors. So this is a purely experimental work, and another challenging area is miniaturization and scalability, where quantum principal component analysis is the important algorithm which we use for as use case for feature extraction, resource limited systems, and can be simulated. The fourth important challenge area is the material and fabrication compatibility, where we use the factorized Hamilton simulation VQE algorithm. And we use this for designing CMOS compatible superconductors or biocompatible quantum materials. Still, it is in early stage and the prototypes are still getting ready. Yeah. So domain specific algorithm gaps definitely are there, which people have to get upskilled and create new algorithms for satellite image classification or biosignal diagnosis or VLSI fault detection. So, audible? Yes. Can I continue? Am I audible?
Yes, sir. Yes, sir. Go ahead, sir. Please go
Yeah.
ahead.
So this is one example, if you can see, quantum machine learning for space research. Okay, so where international university, they have performed this particular operation where they used the measurement of different input data, and they performed some international reference ionospheric research, okay, by performing our normal genetic algorithms, and they simulated using BP neural network, and they got a beautiful results regarding this. As you can see, the predicted results also you can see in the graph. This is one project that the foreign researchers have found. And this is one such an output what they got it in atmospheric science, okay, out of the algorithm that they have developed for northern hemisphere and southern hemisphere. This is one more such a very important project that was simulated in foreign university, where they performed using our machine learning algorithms and quantum principal component analysis. So where they trained the data collected from the TEC observed data, and they trained it properly and modeled it and validated it, and they got very good results. You can see the model block diagram that they have followed. You can see on the top, and how they got the results. You can see on the top right corner in the graphs. So these are the things which Indians, as Indians, our students also have to quickly learn and how to apply these. This is one more results coming out of their work. Okay. So the latest research inventions, if you see, you can see these are the one of the top 5 researchers that I have found out from the literature survey that I carried out. So you can see like quantum machine learning for remote sensing and satellite mission planning. Okay, and resource they have done. Okay, they applied some quantum algorithms applied to satellite mission planning. Okay, yeah. So you can see that they got a completion rate of 98.5% compared to 75.8% where they got using classical techniques. So by that you can understand that quantum computing is more better compared to classical in some of the applications, I can say. I won't say that for all the applications, but for some of the applications, it is giving very good results. Okay, so the second one, if you can see, like a quantum machine learning for remote sensing data analysis there, right? Okay, so you can see here, they also are developing some kernel-based algorithms perform these space-based data analysis. The other important application, you can see the crowdsourced ionospheric mapping using smartphones, and XGBoost for GNSS applications, photonic QML benchmarks. Okay, so they worked a little bit, foreign researchers have done, and they have improved good accuracy, as you can see. how they are going forward. They are trying to scale up hybrid to fully quantum systems and using photonic QPUs, and they're also following for kernel-based quantum classification for geospatial data. Also, the federated quantum machine learning across sensor networks and real-time QML onboard satellite hardware. They're planning for uh, finding out how we can develop some CubeSats for anomaly detection or predictive sensitive directly in orbit, how you can send it. So this is very useful, which we can use in ISRO and NASA also. So quantum machine learning assisted physical modeling of space environments is another important. Similarly, as I said, hybridization of algorithms will give good results. So they're planning to hybrid some QML and quantum machine learning and VLSI CAD tools to get some real-time problems solved, and QNN-based on-chip architectures they're working on, and quantum-inspired machine learning for design automation is the other important application which they are planning for reliability optimization. And also a few members are working on photonic VLSI integration, where they're merging photonic QL modules with silicon VLSI for edge computing applications. So you can see this is another area of research that is getting carried out. Okay, where and why QML? Obviously, to improve speed, efficiency, robustness of algorithms, cross-pollination, and hardware synergy. Okay. Yeah. So another second important use case and application where we have taken is application in biosensors. Yeah, application in biosensors. If you can see the capabilities, like if you take for small sample regression, quantum kernels they are using for improving performance with few data, and we can where we can apply these are like for modeling sensor calibration and biorecognition potentials. So distributed privacy sensitive machine learning is the another capability where federated VQC enable learning across sensor swarms. So where we apply these is for home health networks and environmental monitoring. Third important capability is high-dimensional precision, where kernel-based quantum algorithms and quantum nearest neighbors exploit complex sensor signals, which they're applying in magnetic detection platforms. Also, like explainable AI, we have explainable quantum AI. It's an important capability where they're applying for transparent decision-making with quantum enhanced models so that they can solve some genetic diagnosis and clinical decision support. So the security and anomaly detection, they're applying for quantum supported machines so that to detect sensor tampering more reliably. So where we apply this is for remote monitoring reliability. So this is an important application that you can see where they applied quantum machine learning for biosensors, how they applied this annealing process and quantum design, how they compared with QKA and standard classical loss function in SVR in classical design, how they improved the loss that are observed in classical, how they improved the error rate. Okay, so in error rate in classical was more, and how they reduced it in quantum using QKA. You can see this particular approach that they are applying from that particular operation. So when we are aligning this quantum kernel based regression for semiconductor like biosensors, researchers are developing QKR is a very important algorithm for modeling ohmic contact resistance in GaN. HEMT is using just 159 data points. So it outperformed 7 classical regression models in prediction accuracy. Also, this technique is highly applicable for biosensors with limited training data. It is also useful for modeling surface receptor behavior and calibration curves. So we can apply your VQCs, the classifiers in quantum for your biosensor networks. Also for wearable health monitors, it's very ideal for decentralized biosensing networks. This also protects user data privacy using collaborative learning. It also supports scalability across distributed edge biosensors. Okay, and quantum AI-based nanopore sequencing for genetic mutations is research that people are trying to carry out in IIT Indore. So they developed a system combined quantum transfer theory with explainable AI for DNA sequencing. They are trying to utilize this nano gap-based nanopore biosensors for mutation detection. Quantum machine learning enhances accuracy and interpretability of biomarker identification. So they support real-time high-resolution medical diagnosis. So the best tools, this is what you people are waiting for. We can use D-Wave-based Ocean SDK for quantum annealing. The main task for that, purpose, satellite task scheduling, and path optimization, the use case. Each use case that I mentioned here is a good funding project that you can write it, and our engineering students also have to upskill themselves to work this in industry. Okay, so all top level MNCs are hiring if you are capable in this. Like, and you know, IBM, you definitely know IBM Qiskit, which we generally use for remote sensing data classification. And the TensorFlow, Keras, and TF-Lite are required for onboard AI models for satellite imaging detection. Also, PyTorch and phase transformers are required for classical AI for NLP modeling. And Penny Lane plus Strawberry fields, which they perform using photonic modeling and quantum classical simulation pipelines. So the best tools for biosensors research. So we can use Qiskit machine learning, Penny Lane plus scikit-learn, TensorFlow, federated. Okay, so for biosensor data analysis and calibration, AutoML, AutoKeras using Google Cloud, you can use for fast model tuning of viable biosensor datasets. Also QML Playground via IBM and AWS, you can use for testing custom quantum circuits for biomedical signal processing. The third important one, where best tools for VLSI research, if you can see, you can try our IBM Qiskit for optimization for quantum circuit placement routing. So Amazon Bracket plus D-Wave Leap, you can try for quantum hybrid. Key use cases for VLSI layout optimization, constraint solving. Open Road plus AI plugins, where AI-driven RTL to GDS VLSI analysis automation. Okay, so and Synopsys DSO.ai and TensorFlow plus iGraph AI. These are used for VLSI circuits prediction and optimization. That's all from my end. So there are a lot of things are there. Quantum computing is a big ocean. Name any field in an industry, name any department in a university. Okay, you have scope for performing quantum computing. Okay, you should be future ready to solve those publications. It is not a one-day task. You have to work very hard on this to perform very well. Okay, and to upskill this, you should learn at least minimum linear algebra, Python, okay, and some quantum physics definitely required to perform this. Any doubts are there or any queries, you can please unmute yourself and you can ask. I'm happy to.
Dear participants, the session is open and feel free to raise the questions.
Oh, participants just joined and they're doing their own. It's a problem with online
Dear,
learning. Participants, they join and they do their own work. If no doubts are there, we can conclude, Professor Taskin. They can reach out to me. You can share my email ID to them. They can reach out to me if they have any doubts during funding research projects or any particular thing. I will be happy to help them. Please write me to my email ID.
Sure, sir. Thank you so much for this wonderful enriching session. So we are closing this day with this session. So Sarah has addressed the challenges, integration with the classical system, and the environmental stability and other things and all, material and fabrication compatibility, and some of the algorithms he has explained very beautifully. And he also explored that the various areas where you can put your research thoughts and all. So it was really excellent, sir. And once again, thanking you, sir, for this super session. So I request the participants.
Thank you. Thank you, Professor. Thank you. I'm leaving.
Yes, sir. Thank you, sir. Sir, once again.
Yeah.
So I request the participants please turn on your camera so that we can take one group picture.
Yes.
Okay.
Thank you, sir.
Yeah, thank you, sir. Thank you so much, sir, once again. Okay, thank you, participants. So we are closing today's, and we'll see you in the next day. Thank you. I have shared the feedback link in the chat, so I request everyone to fill it on time. So it will be available only for 15 minutes. It is posted in the chat, so I request everyone to fill it quickly. Thank you.